Hi guys, so today I want to talk about pendulum. So pendulum, you have a string, and then you have a mass. Here you have the center of mass. Now I can displace it by a tiny bit. So you see here it's about 15 degrees, 10, 15 degrees, for example, or 10 degrees. So that displacement is called the angular displacement. Usually this angle is measured in radians. And if I let go, it's going to swing back and forth, right? And I can measure the period, the time it takes for one cycle. Okay? Now, this is called the angular displacement. And you see that pendulum is going to follow a simple harmonic motion only if that angle here that you start with, the amplitude, is small enough, right? So if you have a small angular displacement, then we can show, and I will show you, that it will follow a simple harmonic motion. Okay? So first thing I want to show you is that it does not depend on the mass. You might think, okay, this one should have a larger period than that one. So number one has a mass of 100 gram, and this one, the big one, has a mass of 1500 gram. So you might think that the period should be larger for this one, for number two, than for number one. Okay, so you can you can investigate on your own. Let's try to find the period. Top 1, 2, 3, and 4. Stop. So 8 seconds. Okay, so let's find out for the blue. So now we're going to focus on the blue. We're going to take the same amplitude. Okay, so we are only changing the mass. So let's wait. 1, 2, 3, and 4. Boom. You see it's about the same period. Okay, the other one, I think it was 8 seconds. This one is almost 8 seconds. So the mass does not matter. You can do that several times to convince yourself. So the time it takes to go back and forth is called a period. It's measured in seconds, and the mass does not matter. So it's not too surprising, because remember Galileo Galilei, when he did his experiment on free fall, he found out that two objects, regardless of their mass, will reach the ground at the same time when they are in free fall. Meaning if you neglect a resistance, if they are heavy enough, but this one is much heavier than that one, they will still reach the ground at the same time because they will have the same acceleration. And they will have the same acceleration because this one is acted upon by more weight, but it also has more inertia. This one has less weight, but less inertia, right? So we already talked about that in physics 1. So if you have a mass here, and it's falling, it's in free fall, and it has here big mass, so it means large weight on Earth, and there is no resistance. So we can say that the weight, it's the only force acting on it. So down is positive. It has also a big inertia. So they're going to cross each other out, and the acceleration is just g, which is 10 meters per second. Likewise, if you have a small mass, if you neglect a resistance, so the weight is the only force acting on that small mass and it's falling down, you also have a small weight but small inertia, so you get the same acceleration. So that's why when Galileo, again, when he was 17 years old, the story says that he was at church, maybe he was bored, maybe the sermon was too long and it was boring. So he looked at those censer. You put incense inside and you burn them, and they are hooked here at the ceiling and they start to swing back and forth. Actually, I have pictures here, so they are attached to the ceiling and they're going to swing back and forth. And he noticed that the the period it took to go back and forth, as long as they had the same mass. You have several of them in a church here. Maybe you have a small one and a big one. They both had the same period. So I don't know if the story is true, but what is true is that when he was only 17 years old, he started to investigate those pendulum and he reported his finding. So is it surprising that the mass does not matter? It's not surprising because we know that when an object is acted upon just by gravity, then the mass will disappear, right? The acceleration will be the same. And it can be falling straight down, or it could be falling on an inclined plane. So this is an inclined plane. It was also designed by Galileo Galilei. And he found out that if you have a heavy mass here or a small mass, for both of them, the time to get down will be the same, right? Because the acceleration will be the same regardless of the mass. So even though it's not falling with 10 meters per second as an acceleration, they will still have the same acceleration. And by the way, you see here what you have, it's a pendulum, right? So he used that. Once he understood the pendulum, then he used that as a stopwatch. You can use a pendulum as a stopwatch. So that's for the story. Okay, let's go back to the lab. So the period is the same regardless of the mass. So let's go back to this one. Let's compute the period again. 1, 2, 3, 4. So about 8 seconds, right? Let's see what's going to happen now if I decrease the length. So it's the red one now. I want to have a small length. What's going to happen? So keep the amplitude the same. I don't know where I was. Maybe I was here. You see? It's going to swing faster, right? So let's find the period. 1, 2, 3, 4. Stop. About 5.65 seconds versus 8 seconds. So the period of a pendulum, so the mass does not matter. So that means the period that we're going to find is going to be 2 pi because it's a simple harmonic motion. Then we're going to have something here with a square root like the spring, but we know there is no mass here. That's we know. What else do we know? We know that the period is going to decrease when the length of the pendulum is increasing. What else do we know? Let's see if we change the amplitude. This is going to change. So let's go back to my length of 1 meter here. Let's take a larger amplitude, but not too large, just a little bit larger here, like this one here. Let's see here, 30. Even at 30, right? 1, 2, 3, 4. Stop. 8 seconds. So the amplitude does not matter. Okay, so here we do not want amplitude. So no amplitude, or we can say no angular displacement max. Okay, so we can say the angular displacement in radian max, it does not depend. So you're not going to find amplitude here, you're not going to find the mass, you're going to find the length. So if you want t to decrease, so we want t to decrease when the length t decrease when the length no, it's the opposite, right? So when the length increases, the period increases. Okay, so we said for length here, in our case here, sorry, in our case, when the length is 1 meter, we found 8 seconds. And as you decrease the length, so if I make a very small length, you see it's gonna, you can see it's swinging faster, right? So now we know that if the length increases, the period increases. So we're gonna put the length here. So I'm missing something. It's not the mass, it's not the amplitude, something else is there. So let's look at the amplitude. Can you see something else I can change? So there is no friction. I can change something else. I can change gravity. So this is on Earth, obviously. But if I increase gravity, you see the period is going to increase by a lot, right? I don't need to do the stopwatch. You see that gravity does influence it. And what's fun is if you remove gravity, you so it has inertia, so it keeps going forever, right? So here we can say we can put gravity here. So that's going to be the period of a pendulum. So Galilei found out that there was a relationship between the period and the length of a pendulum. Okay, so t is the period, is in second, the length is in meter, and g is gravity, and it's meter per second per second. So what is cool is that he understood, even though he didn't have this relationship yet, but he understood that through experiments, he understood that you can use a pendulum as a stopwatch. And the rule to remember is simple. If the length is 25 centimeter, so you take a string, and you make it 25 centimeter. I don't have a ruler here, but if it's about 25 centimeter, oh, okay, I broke my thing, but if it's about 25 centimeter here, and you have a weight there, the period will be exactly 1 second. So 1 second. So you can use your pendulum to make a stopwatch. Okay, so let's find out. That's what I claim. Let's plug it in. So T equals 2 pi. The length here is, let's say, 25 centimeters. So gravity, I need to use centimeter per second. So it's going to be 980. Okay. And if you do that computation, you get 1 second. So if you make a pendulum about that large, 25 centimeter, I encourage you to do it on your own. So if this is 25 centimeter, it will take exactly 1 second to go back to the same position. Exactly 1 second. So I don't know if you can do that here. If the length is 25 centimeter, and I displace it here, let's say. I don't have gravity. So let's see. Let's take a smaller mass because I don't see the thing here. It's easier. Let's make it slow. So I am at 25 centimeter. Stop. So that's gonna be half, and that's gonna be boom 1 second. Isn't that amazing? So if the string is 25 centimeter, the period is 1 second. Okay. So what else do I want to show you? Let me see. Okay, so let's go back to vectors. Here. So in yellow, you have the acceleration. And you see that the acceleration is large, it goes to 0, then it's large, and then it goes to 0 here, and then it's large. Let's make it slow. Okay. So let's look at the forces now acting on that mass. So let's say it's swinging, right? So you have the center of mass, and it's describing a circle here, and the length is L. So the circle has a radius L and swinging back and forth. When it's at equilibrium, so let's say it's not moving, you have your mass here, M. When it's not moving, you have the weight here pulling down, so mg, and you have the tension up. So if it's not moving, T equals mg. So then you displace it here. So you have a angular displacement theta, which is in radians. So you move it a tiny bit, and then it's going to start swinging back and forth. So that position here, it's hard to draw, but if you have the tension T, so you still have the tension T, but the tension T, you see, is perpendicular to the trajectory. So it does not change the speed. Does not change the speed. All it does, it wants to keep the mass on the track. So it's going to be involved in finding the centripetal acceleration, but it doesn't make the mass go faster or slower. It doesn't make it go faster here. It doesn't make it slower, make it go slower when it comes back. So I'm going to call that the x-axis here, and because that's the one you are most used to. And then you have the weight. Okay, so you can throw the weight on your own. The weight's going to be straight down here to Earth. And with a little bit of geometry, if this is the angle theta here, you see that's going to be the angle theta here. So you see that weight here has two components. It has, and each component has a different job. So that's the x component here, and has a y component here. So along the y, we are not very interested what's going on. You see that T is pointing toward the center. The y component here of the weight is pointing away from the center. And then you're going to have a centripetal force. So this is just to keep the mass from flying off. That's not very interesting. But here you have the x component of the weight. So the x component of the weight is interesting because this is actually, this is your restoring force. Okay, that's your restoring force, because you see the x component of the weight here is very large, and then it's going to decrease here. It's going to get to 0. No more x component, and then it's going to increase again, but it's going to pull in the opposite direction, the x component of the weight. So this is your restoring force. So remember, same thing for the spring here. When you had the spring here, Here it's happy, it's at its equilibrium. And then you pull the spring. Here, maybe it's there now, and then it starts to oscillate back and forth. That's what that was called the displacement X. This is your X-axis. Here, maybe it's going to be positive. So let's say it was moving in this direction. So that will be your acceleration along the X. And then you had a restoring force in this direction, right? So you have F equals minus Kx. And because the restoring force is proportional to the displacement, so this is a simple harmonic motion. And remember from last unit, T was 2 pi, and then here you had a M and a K, large M, large period. And we also define the angular frequency, 2 pi, and then there is a K here, and there is a M. No, there is no 2 pi. There is just square root. So this is the angular frequency, just how many radians in seconds, right? We'll get back to that, but that's what we did last time. So let's see if we can get something similar here. So the X component of the weight, first of all, the X component of the weight, it's going to be the weight. Here, this is your weight. Here, this is your weight. So it's going to be the weight, so mg. So sometimes it's capital. So that's a small m. So mg. And here you have theta. So mg sine theta. So it's, and I should put a minus here. Okay. This is positive, and let's say it's swinging in this direction here. So the restoring force is opposing. So it's pointing in the other direction. But then I told you that theta is relatively small. And if this is the case, sine theta is about equals to theta in radians. So for example, if you do sine 15, you get 0.26, right? Now, if you do 15 in radians, so 15 degrees, and you have pi is the same thing as 180, so that will be in radian. So that's going to be 0. So the restoring force equals minus mg theta. Okay, it's for small angle. And so you see that it is a simple harmonic motion because you have the restoring force. So it's the restoring force proportional to the displacement. Except here, it's the angular displacement. But from angular displacement, we could go to the linear displacement, right? So if we take a small delta x here, if that delta x, say, is not that big here, we can say that delta x equals r delta theta, okay? Or small displacement x equals r theta, or x equals l theta, right? So you go from angular to linear. But that is the proof that a pendulum can be approximated as a simple harmonic oscillator. Okay? So let's go back to here. So the period is the time for one cycle. The frequency is 1 over the period. Okay, so it's going to be 1 over 2 pi square root of k over m. It's the number of cycles per second. And omega is what we call the angular frequency. Okay, so it's going to be 2 pi over t. So the angular frequency is just the number of cycles the number of radians per second. So for example, if you have 1 cycle per second, that means you go around in 1 second, right? So omega will be just 2 pi. So 2 pi rad per second, because in 1 second, you're going to go 2 pi radians. Let's say the period is 2 seconds. So omega will be 2 pi over 2. That's going to be pi. So that means in 1 second, it's doing half of a, in 1 second, it's doing half of a cycle, or pi radians, right? So that's the meaning of this angular frequency. Okay, why am I telling you that? Because if we look back here, if we look back our spring, here, and let's write down the net force equals minus kx equals the mass times the acceleration. Okay, the acceleration along the x. Now I can write mass times acceleration plus kx equals 0. And I don't want any coefficient here, so I can write that as the acceleration plus k over mx equals 0. And what do you see here? This is your angular frequency square. Okay, because the angular frequency is square root of k over m. So when you have a simple harmonic oscillator, then when you write down the equation of motion, so it's just Newton's second law, net force equals ma, whatever is in front the coefficient next to the displacement here, that's going to be the angular frequency. And again, the angular frequency is just 2 pi over the period, okay? So it's just the number of radians per second. So let's see if we can apply that to the pendulum. So the pendulum, I have that, right? So I have the restoring force equals the mass times the acceleration. So I'm going to write the angular acceleration along the x. Okay, so I have mx plus j theta equals 0. So here I have the theta, and here I have a linear acceleration. So I'm going to write down that theta equals x over L. Okay, so if I do that, and I had a mass here, so if I do that, so first of all, the mass goes away, which is nice, because remember, we know that the mass does not matter, so it should go away. So we have acceleration plus gx over L equals 0. So therefore, that's going to be my angular acceleration. So the angular acceleration is g over L. Okay, so this is called the equation of motion. If you are taking calculus, then you can write this, or let's say this one here, you can write that one as, this one here, you can write it as the second derivative plus k over m x equals 0. Okay, and we're going to see in the coming lecture how to solve for x. But this is a simple second degree differential equation. And you see that you get exactly the same form here. Okay, so sometimes in that case, for the pendulum, you don't want to be, you want to stay in the angular form. So that means you're going to say, I'm going to stay here, so I'm going to be, so acceleration plus g theta equals 0. And this is here, it can be written as L, and that's going to be the angular acceleration. So I'm going to say L theta dot dot plus g theta equals 0. And you get the same type of equation. Okay? But not to worry if you are taking the MCAT, not to worry about that. But it's just nice to understand that as long as your restoring force is proportional to the displacement, then you have a simple harmonic motion. Okay? And that's going to be the equation of motion. Okay. That was just a parenthesis. So here, that's how it's written here. You see, you have the X component of the weight, that's your restoring force. The Y component here is busy with the tension to provide a centripetal acceleration. Okay, so that's going to be the angular acceleration. We'll get to that in a coming video. Well, let's try to do some problem now, some conceptual question. I'm just checking to see if I told you everything I wanted to tell you. Okay, so let's see. Let's do this one. And of course, you want to, so that will be typical question, for example, for the MCAT or conceptual question for AP physics, for example. So let's try to answer this one. So you have different way to solve those. So here, 1/4. So you see the period is 2 pi, and then it's going to increase with the length and decrease with gravity, right? And now you have a new gravity, which is 1/4 gravity on Earth. Okay, so you can do it algebraically, or you can do it with numerical examples. So let's see, the new period equals 2 pi L G prime. And the old one equals 2 pi and then the square root of L over G. So you have different way to do it. So you can say, okay, what's happening here? G prime is divided by 4, right? Here, this is divided by 4. So 1 over G prime, it's going to be multiplied by 4, okay? And then you are taking the square root. So 1 over G prime, L doesn't change, so it doesn't count. It's going to be multiplied by 2. So the new one, the new period is going to be doubled. Okay, how can you do it a different way? Different way, you can give yourself numbers. Okay, you can say, okay, let's take L equals 1. That will be easier. And G, okay, I know we are on Earth, but let's say you are on a planet with a gravity equals to 4 meters per second, right? To simplify, because then you know it's going to be divided by 4. So T equals 2 pi, and then you have the square root of 1 over 4, which is equals to 2 pi over 2, which is pi. Now, with the new G, you see L equals 1 meter, and G prime is divided by 4, right? 1/4. So new is 1 meter per second. So the period will be 2 pi, and then 1 over 1, which is 2 pi. So the new one is multiplied by 2. You get the same thing. Okay? Other way to do it, you have 2 pi L over G prime. That's the new one. And then T equals 2 pi L over G. So you take the ratio between them. So you have T prime over T equals 2 pi divided by 2 pi. Okay, so it goes away, can cross. And then you have L over G prime times, when you divide, you multiply by the reciprocal, so G over L, cross. So T prime over T equals, what is left is the square root of G over G prime. And G prime is 1/4. So it's going to be G over 4. So it's going to be square root of 4. So it's going to be 2. So T prime equals 2T. So maybe this way here is the easiest way. This one, if you're used to it, is also nice. This one works well when you have actually numbers. So it's typical conceptual questions. So what happens if the length is multiplied by 4? Let's see. What happened to the period of pendulum in the length is multiplied by 4, so T equals 2 pi, then the square root of L over G. So if L is multiplied by 4, what's going to happen? The square root, here you have a square root. So the square root of L is going to be multiplied by 2. Okay, so T is going to be multiplied by 2. Right? And the other way around, you can say, okay, if L equals 1 meter, let's say G equals 1 meter. So the period equals, let's give us fake numbers. It's going to be 2 pi. What's going to happen now if L is multiplied by 4? So T equals 2 pi, and then you have square root 4, because it's 4 times 1, divided by 1. So that's going to be 2 pi times 2. So we get the same thing. The period is double. Okay. So this one, I think this one is easy. So you have the period. So T equals 2 pi over L over G. Okay, so let's square both sides. So T squared equals 4 pi times L over 9.8. And the period is 1. Oh, but we already know that, right? So 1 equals 4 pi squared times L over 9.81. And I told you we should get 0.25 meters. Okay, because a pendulum with a period of 1 second has a length of 0.25. So 25 centimeters, right? So if you have a pendulum, if it's fixed here, if you have a pendulum, and if it's about 25 centimeters, I don't know how, 25 centimeters, the period should be 1, regardless of the amplitude. 1, 2, 3, right? And if you make the length shorter, right? So let's say this is my pendulum here. I don't know if you can see. This is my pendulum here. If I make it shorter, you see how it's speed up and now it's slowing down. So this is very slow. And then I decrease the length to see how the period is smaller. Okay, so then we have all those problems to do. I think they are easy. They are very easy. So I don't know if I should do it or not. Let's see. You should pause the video and try to do them. Let's do a few of them. Okay. So here you have the period and you have gravity. It's on a planet 3.79 and you want to know what its new period if you change gravity. Okay, so you have the period equals 2 pi the length over g. And the length is the same. So one way you can do it, so that will be your new period, new gravity. This is the old period, 2 pi, the length is the same, g. Okay, you can divide the two equations. If you don't want to do that, if you want to do it the long way, you can first start here, solve for L, and then plug L back into this one. So that will be the long way. Okay, so if it's easier for you, you can do that. You can plug 9.79 here, solve for L because you have 3, and then you plug L into here and you find the new period. Or you can divide the two equations equals, you have L over G prime, you multiply by the reciprocal, so it's going to be G over L. So T prime over T equals, and then that goes away. You have G over G prime. So it's the square root of 9.79 over 9.82. And the ratio that you find is I don't know. I think I found 0.99, something like this. That ratio here. So the new period is about 2.99 seconds. So you see that it does not change much, right? You just have a decrease by 0.5% relative to this. So it means gravity, you don't see really the effect unless you change dramatically the gravity, right? Because it's not much of a difference between 3 and 2.99 seconds. And of course you can play here, you see 9.81, I decrease a little bit gravity, you know. It's not much of a difference. You really have to go very small to see the difference, and or very big. And here you have no gravity. So here again, it's pendulum are great for those kind of conceptual questions. What happens if I do half the length? What happens if I do twice gravity? So it's good. It's good. It's a good training for problem solving. So you have the period depending one half. So the length is divided by 2. So you have different way to do it, right? So the period equals 2 pi, and then the length here, and then you have gravity. So if the length is divided by 2, that's what it says. Okay? So that means the square root of L is divided by the square root of 2. So the period is divided by the square root of 2. Okay? So that means the new period will be the old period 3 divided by the square root of 2. Which is 2.1 seconds. So you see that if you change the length, you do have a big difference in the period. That was the point. You have a different way to do it, of course. So this is easy. The only thing that is a little bit tricky, they give you the mass. But we know that the mass does not matter because it's like it's falling, right? When you have a pendulum, it's like the mass is falling. So the mass does not matter here. You still have the period equals 2 pi the square root of the length over g. And so this, we don't care. This is 2. And this is 9.8. So you can find the period. You can find the period in seconds, right? And I don't know what you find. You can do it. So square root of 2 divided by 9.8. And then you multiply by 2 pi. And you get 2.8 seconds. Okay, so the next one is interesting. You have this, you have a spring that is oscillating here. And it says 7 kilogram. And the spring constant is 88.8 Newton per meter. And then you also have a pendulum. And and they have the same frequency. So that means they have the same period, right? So here the length is L. So they have the same period and they have the same frequency. So the period here is 2 pi So the mass, and then here we have K, which is equals to pi, and then we have L, and here we have G. So that goes away. So that means that M over K equals L over G. So we have L equals M times G over K. And if you plug numbers in, you should get 0.77 meters, which is 77 centimeters. Okay, so this one is not bad. Number 5, I think all those are easy problems. It's not very challenging. So mass, you have G equals 3.75. So on Earth, the length is L, and so you want to change the length on Mars so they have the same frequency. So same frequency means the same period, right? So on Earth, we have 2 pi, and then L, and then on Earth is 9.81. Okay, and we want the same frequency, but on Mars. So L prime, and here we have 3.75. So whatever is under the radical should be equal to each other, right? So we have L prime over 3.75 equals L over 9.81. So L prime, so the new length over the old length equals to 3.75 over 9.81. So it means we have to make the pendulum shorter because you don't have enough gravity, right? Relative to the Earth. You have less gravity relative to the Earth, so you have to make your pendulum shorter to compensate. And if you do that, that's going to be L prime is about 0.30 L, so 38. So that's 38% of L. So it has to be smaller. And you can look at this here. You can change gravity. I don't know why it's not. Oh, I have no gravity, right? You can change gravity if it has a very small gravity. What you can do, we can change the length. Then it's gonna swing back and forth faster. Okay, so this is easy. And that is easy also. So frequency is just 1 over the period, right? But it's an easy problem here. So you have the length here, so 0.05, the frequency. So you have the frequency is 1 over the period. So it's going to be 1 over 2 pi. And then here for the period I had L, so now I have G over L, right? Because the frequency is 2 pi L over G. That's the period, sorry. So the frequency is going to be 1 over 2 pi. So that's going to be 1 over 2 pi. Then you take the square root of 10 here. And this is 0.05. Okay. And so you can compute that, and the frequency will be cycles per second or hertz. Okay. So you have period. The period is 1 over the frequency. The angular frequency is 2 pi over the period, which is equals to 2 pi times the frequency. And again, this is the number of radians per second. Okay, so here I have a link to a video, and it's just that if you want to review, it's a YouTube video, it's a channel for physics, and this problem could be nice because it's reviewing the conservation of energy, which is not really the topic here because this is swinging back and forth between kinetic energy and gravitational potential energy, but it's a nice review. So I recommend to watch this video, and I recommend this channel. It's a very nice channel. So if you're reviewing for the MCAT, it's a good idea. So here is another type of pendulum called the torsional pendulum. It's when you can twist, right? So you can apply a twist here, you can apply a torque, and then you're gonna let it go oscillate about its equilibrium, oscillate back and forth, right? And you see you have exactly the same kind of equation of motion. You have the torque applied, so you need to apply a torque to make the twist. That will be equals to the angular inertia, or the moment of inertia times the angular acceleration. And you see that the torque is k times theta, so that will be the small displacement relative to the equilibrium, and so that means that's going to be the restoring force. So that means it's also following a simple harmonic motion. It's a simple harmonic oscillator. And same thing here, that whatever is it, that coefficient here, 2 pi times the square root of this, that's going to be equals to your period. Okay. And another interesting thing is what we call the, I don't know if you can see on the camera, so this is called the physical pendulum. So you see it has a center of mass somewhere there. Yeah, the center, not at the center, but somewhere there is a center of mass, and you can displace it a tiny bit here, a small angle, and it's gonna oscillate, right, about its equilibrium, and it will also follow simple harmonic motion. So this is called a physical pendulum, and you apply. It looks more complex, but it's not. You apply exactly the same principle, right? So you can have a weird shape here, something like this, and this is your shape. Somewhere here you have the center of mass, so you displace it a tiny bit. Okay, so now I don't know how I'm going to make that weird shape here. It doesn't look the same, so it's okay. And it's going to swing back and forth here. And the restoring force, again, it's because you have the weight here pulling down, mg, and you also have a force from the pin here, but it doesn't matter. And then we can call that distance here r. And then you go back to the physics about rotation. And that angle here, theta, that's the same angle theta that you have here. So the torque applied by mg, okay, equals the moment of inertia times the angular acceleration. Okay, so I'm going to call that alpha. This is the angular acceleration. So the torque, I'm going to put a negative because it's a restoring force. So that's going to be mg sine theta. That will be the lever arm. So that's going to be R equals I alpha. This is just to give you an example. It's not covered by the MCAT. That's fine. Just to give you an idea how it works. This is about theta if the angle is small. So you're going to have minus mg theta R equals the moment of inertia alpha. So what matters here is that this is the restoring force. Okay, and you see that the restoring force is proportional. It's proportional to the displacement, to the angular displacement. Alpha, theta, sorry, that's theta. So that means it's going to be a simple harmonic oscillator, right? So I can write that equation as this is here, that's my acceleration, okay? This is my acceleration, except it's an angular acceleration, plus mg r theta equals 0, okay? So I divide both sides. So I'm going to mg r, and then you have the moment of inertia, theta equals 0. So the moment of inertia depends on the shape. So what do you see? That you also have an angular frequency equals mg r over I. So you might be surprised here. You say, okay, but how come I have an m? But the m will disappear once you find the moment of inertia. For example, if you have a pendulum, the moment of inertia is just mr squared. So if you plug that into here, you have mgr over mr squared. Goes bye-bye, that goes bye-bye, and you get your equation here. That will be just the length of the pendulum. So that was just a parenthesis. And so next time we'll go into the cosine and the sine and the equation of motion. I hope it was not too long.